This is William Dillon, an associate professor in electrical engineering at the University of Texas at Arlington. Today, we're going to begin our first lecture on complex numbers. This is about the basics, very basics of complex numbers. To be complex, a number must have both not only real but imaginary parts. The imaginary number is based on a concept that may seem a little strange. It's about having the square root of -1. And we call that I, the mathematicians do anyway. In electrical engineering, we prefer to use small case j rather than writing square root -1 and all that. And we like to use j because little I often means instantaneous current when we're talking about circuits. So to avoid the confusion, we stick with j. Now, a complex number will consist of a real number and an imaginary number, such as this example where we have z is defined as the real part of 3 plus an imaginary part of 4. The j means that it's the imaginary part. A useful concept is to think of complex numbers as being on a two-dimensional coordinate system, where the real axis, the old x-axis, represents real numbers. The imaginary axis is on the y-axis, is representing the imaginary values. For example, py would be this projection on the imaginary axis. Px is the projection on the real axis. When you draw a line from the origin out to the points, px, py, then you get the hypotenuse of a right triangle here, and that right triangle with its hypotenuse has a length and an angle. Now that's how we get the polar form of the complex number. So we can switch back and forth. And so if we have, for example, px and py as a complex number that starts off in rectangular form, px has got to be the magnitude, that's that hypotenuse that we looked at, times the cosine of the angle theta. And py is that magnitude times the sine of the angle theta. Now, when we do this, we can factor out the p values and factor it out to be the absolute value of p multiplied by cosine theta plus j sine theta. Now, that becomes a complex number with a magnitude of 1 at an angle of theta. The same thing can be represented as magnitude, absolute value of p, times e raised to the j theta power. Now that's equivalent to the polar form that we saw earlier. Now e, we must remember, is the basis of the natural logarithm, 2.718 or so. And theta in this configuration, when we actually evaluate this exponential, needs to be in radians. So here's how Euler's formula is actually evaluated, how we get e to the j theta. To do this exponential, then we have an infinite summation of j theta to the k power over k factorial, where k goes from 0 up to infinity. We usually don't have to go very high. Normally, this converges rapidly in a few terms, and so that we can find these things without computing forever. And it's interesting how it works out, though. Let's look at a few terms. Let's start with k equals 0. Well, by definition, 0 factorial is 1. And by the way, factorials are found by taking k times k minus 1 times k minus 2 all the way down to where k minus something is 1. And so it grows rapidly as we increase k. That's why it converges so quickly. Now, j theta raised to the k power, remember k's are always integers here, then we're going to get this series that looks like you see it here. Now, let's look at a few terms. When k was 1, we're going to get 1 over 1, and that's a real number, and that shows up in a group of other real numbers, and we'll add to that. Let's look at the second term when k is equal to 1, and we'll have j theta times 1 over 1 factorial. That means that we would get just j theta. And we'll factor out the j. We're going to factor out all the j's, and we'll put it here. We'll put the theta value there. That comes from the second term. In the third term, where k is actually equal to 2, we're dividing by 2 factorial, which of course is 2, and we're going to have j theta squared. Well, j squared is minus 1. Okay, therefore, this is going to be a real number, theta squared, but negative because of the j squared. And that's our next term. And that is a real number, so it goes here, and it's minus. Let's look at the third term, or the next term, actually the fourth term, where we have k equal to 3. And we're going to divide by a 3 factorial. And if we take j cubed here, j cubed is minus j. So that's another negative, and it's got a j that's been factored out. And that's our term down here for the sign collection. And if we go to the fourth power for k, we've got theta to the fourth over 4 factorial. And what happens to the j here? Minus j to the fourth power is a plus 1. Okay, so that's a positive real for that term. And as you can see, as we keep on moving out with this, when we go to the higher numbers of k and so forth, that we can collect all the even numbers, even values of k. They'll all have real components, and so we'll call those cosines. Notice the sign alternates. On the other hand, if they're odd, we're collecting up signs, and they're imaginaries, and they also alternate sign, minus, plus, minus, and so on. And so that shows that this whole infinite series turns out to be cosine theta plus j sine theta. That's what we get from this. That's why we can use e to the j theta to represent this, cosine theta plus j sine theta. Now keep in mind again, theta in this equation is in radians, where there are 57.29 radians per degrees per radian. There are 2 pi radians in a complete circle, and so 360 degrees is equal to 2 pi, and you can work out the ratio there. So remember that if you have to calculate this, and you won't, your calculator does that for you. That's where it came from, though. And so Euler's formula is used to define the complex number where we can do it in rectangular or polar form. And now you notice that we've actually got 2 polar forms, if you want. This e to the j theta deal is really just the same thing as saying angle at theta, except when we do this second middle term here, we often just leave theta in degrees for convenience.